the production of high energy emission in AGN jets by the interaction of massive stars. The talk is very simple. First, a brief introduction about AGN, then the description of the jet-star interaction, and the development of non-thermal processes, and finally some conclusions. This work is part of the most general study about the interaction of relativistic jets with obstructions from the external medium. And we want to study this scenario in order to explain the gamma ray emission, the steady and variable gamma ray emission observed from high mass microquasars and AGN jets. In particular, we have a study in high mass microquasars. As you know, these high mass microquasars are binary system composed by a black hole with jets and a companion massive star. And the winds of massive stars are not homogeneous. These winds are clumpy. And so in this scenario, we studied what happens when clumps from the companion stellar wind reach the jet and interact with this relativistic plasma. Then in AGN jets, we study also the interaction of clouds from the broadband region, also with the jet of the AGN. And now I will present the last study about the interaction not of cloud, but the interaction of massive stars with jets in AGNs. Well, AGNs, you know, are systems composed by a supermassive black hole that accretes matter through an accretion disk, and a small fraction of this matter is ejected and forming these bipolar outflows of relativistic plasma. And as you can see in this famous picture, these sources are extremely anisotropic. So the phenomenology that we see from these sources strongly depends on the leading angle. In particular, if we see these systems in this direction, the system is called blazer, and in this situation, the emission produced in the jet is strongly amplified by the combustion. And as I will show then, our model is applied for non-blazer sources, because in the model that I will explain later, the meter is not moving with the jet, so the meter is not moving at relativistic velocities. For this reason, the emission produced there is not amplified. And all this particularity of this system is that produce emission in the whole electromagnetic spectrum, from radio to gamma rays. And emission could be continuous and line emission, and also thermal and non-thermal. So in order to study the interaction of massive stars with jets, we start our study studying what is the population of massive stars around black holes, supermassive black holes. In this, assuming an observational relation between the star forming rate, the star formation rate, and the mass of the black hole, we estimate what is the number density of massive stars around a supermassive black hole, and assuming also two different power laws for the dependence of the density with the distance to the black hole. We assume that these power laws are the density follow this relation with the distance -1 and -2, and we plot here the number density of massive stars from 1 parsec to 1 kiloparsec. We start in 1 parsec because closer to the black hole, closer to 1 parsec, it's very difficult to form massive stars, because the tidal disruption of the black hole disrupt the molecular cloud before the formation of stars. For this reason, we start at 1 parsec, and we have massive stars from 1 parsec to 1 kiloparsec. And well, here these lines that decrease with zeta are the number density of massive star. This plot is for a power law equal to minus 1, and this is for the power law equal to minus 2 is this relation. And for different masses of the black hole and different accretion rates, because the star forming rate depends of the accretion rate of the supermassive black hole. And then we integrate this density, this number density of massive star in the volume of the shell, and obtain this expression for the number of stars that can be continuously into the shell. So if we integrate this, as I mentioned before, if we integrate this density in the volume of the shell, we obtain this expression also for a power law equal to minus 1 and minus 2. And this, and as can you see here, the number of stars into the shell increase with zeta. Why? Because the shell is, we are assuming that the shell has a conical geometry, and so the shell is larger at larger distance to the shell than closer to a larger distance to the black hole than closer. And for this reason, the number of massive stars into the shell increase with zeta. Then when we put a massive star with a strong wind into the shell, we can, this working surface is formed. We have a massive star with a strong wind, and also this is the shed flux, the shed plasma. And when the run pressure of the wind is equated with the run pressure of the shell, this contact discontinuity is formed here, and also a shock is formed in the wind, and another shock is formed in the shell. And we have this structure that is not steady, because given that the density here is different to the density here, maybe after some time this contact discontinuity will be disrupted by hydrodynamical instabilities like Rayleigh-Taylor. But we are developed our study in the steady situation. So when this is steady, we have two shocks: this shock in the wind and the other shock in the shell. And in this shock, we can accelerate particles via diffusive shock particle acceleration. This is the famous Fermi mechanism. And we're interested to do that because we want to estimate the non-thermal emission. And to estimate the non-thermal emission, we have to know what is the population of non-thermal particles. So in the Fermi acceleration model, we have a shock and some kind of magnetic instabilities in each side of the shock. After some time, this population, of particles is injected behind the shock, and this population is like a power law in energy with an spectral index with an index equal to -2 or -2.2. This is a theoretical result, and we are assuming this value 2.2. These particles that are injected behind the shock can escape from the emitter and also can emit radiation, non-thermal emission. And so if we solve this Fokker-Planck equation, we can obtain this distribution that is n, that this is the number of particles of relativistic electrons. This is the injection function, and this is the energy distribution of electrons. And we want to obtain this distribution, that is the number of electrons, or relativistic electrons. But to solve this equation, we know this function, that is this, but we have to know what is the rate of energy losses by radiation and also by escape. For radiation, we assume the most important radiation channels are synchrotron and index constant scattering, and for synchrotron we have to know the magnetic field. to estimate the magnetic field in the shed, we assume that the magnetic energy density is a fraction of 0.3 of the kinetic energy density. And this is a theoretical result for AGN sheds. And for the magnetic field of the wind, we assume the parameterization of the wind given in this article, with this value of the magnetic field in the base of the wind, at the base of the wind. But this is a safety parameter because this value is not well known. Also, we obtained the maximum energy of electrons. That in the case of electrons accelerated in the shed bow shock, this maximum energy is constrained by synchrotron losses. And in the case of electrons accelerated in the wind, the maximum energy is constrained by inverse Compton scattering in the quantum regime and by diffusion losses. This is the maximum energies at different zetas from 1 parsec to 1 kiloparsec. As can you see in this, as you can see in this picture, the maximum energies increase with zeta. Yes, if we put a star into a shed at 1 kiloparsec, the population of relativistic electrons accelerated there can reach energies larger than here. This is because the emitter is larger, so the escape losses are larger, and the magnetic field is lower here because the magnetic field decreases with zeta. And in the case of the wind, of particles accelerated in the wind, at the small values of zeta, the maximum energies are constrained by inverse Compton scattering, and at larger values of zeta, the maximum energies of electrons are constrained by diffusion losses. To estimate the maximum energies of the population of non-polar particles, we compare the energy gain by acceleration mechanism, by the Fermi mechanism, with the energy losses. When the gain is balanced by losses, we obtain the maximum energy of the distribution of particles. So, once we know the magnetic field, we can put here the energy losses by synchrotron and inverse Compton and solve this equation, and we obtain this number of electrons in energy. Also for different values of the black hole mass that is associated with the shed kinetic luminosity, because we assume that the shed kinetic luminosity is a fraction of the Eddington luminosity, and we assume different fractions, 0.1 and 0.01. And we obtain this distribution of electrons. Also, these are for one star located at 1 parsec, and for 3 different values of the shed kinetic luminosity, and this is at larger zetas. This case is for the shed, and this case is for the wind. As you can see here, the spectrum of electrons at low energies is determined by advection escape losses, and at larger energy the spectrum is determined by inverse Compton losses in the Thomson regime here, and here this feature here is the effect of the Klein-Shiner regime. Well, once we know the energy distribution of electrons, we can compute the emission of these electrons. The most important emission channels are synchrotron and inverse Compton, both in the shed and in the wind. Here we plot the synchrotron emission produced by only one star interacting with the shed at 1 parsec in red, 10 parsec in green, 0.1 kiloparsec in blue, and 1 kiloparsec in violet. We note that here at 1 parsec from the shed, the emission is larger than 1 kiloparsec. This is because the target for the radiation, that is the magnetic field in the case of synchrotron emission, and photons, the density of seed photons from inverse Compton, is larger close to close to the black hole than at larger distances to the black hole. For this reason, the emission that one star can produce close to the black hole is larger than if we put the star at 1 kiloparsec. That is these violet lines, both in the shed and in the wind. So this plot is for only one star interacting with the shed at 4 different locations. And synchrotron and inverse Compton in both cases. Then we put a star at more different distances and we integrate the volumetric luminosity. Here in these violet lines is the integration of the volumetric luminosity from 1 parsec to 1 kiloparsec in the shed and in the wind for the interaction of only one star. But then if we multiply this for the number of stars into the shed, the luminosity increases very much because the number of stars, as I plotted in the previous slide, in the first slide, the number of stars into the shed increased with the distance to the shed. For this reason, at larger theta, the emission produced by all of the stars into the shed is larger than the emission we have here, because here we have only a few stars and here we have a lot of stars. And this is the volumetric luminosity. These two plots are for the shed and for the wind for only one masses of the black hole, 10 to 9 solar masses. But these different lines in red we plot the case of the stellar distribution. In the case when the stellar distribution follow a power law equal to -2 with distance, and in red when the density of a star follow a power law equal to -2 with distance to the black hole. And in both cases, different lines are for different accretion values, accretion of matter to the supermassive black hole. And finally, we integrate the emission, not the volumetric emission, but the emission, the spectral energy distribution at different zetas. We compute this at more distances and integrate along the shed, and we obtain this total spectrum. Also, for the case of the mass of a black hole equal to 10 to 9 solar masses, and for different values of the accretion rate, and also for different values of the shed kinetic luminosity. And this is the total spectrum that we can see from a shed when a population of massive stars is interacting with the shed. This is synchrotron emission and this is inverse Compton emission. Well, and finally the conclusions, we study this because this scenario of shed-star interaction is an alternative to explain the gamma ray emission that Fermi is detecting from misaligned AGN sheds. In the case of misaligned or non-blazar sources, this scenario can produce significant amount of gamma rays that can explain the observation, and we propose this model as an alternative to explain the production of gamma rays in AGN sheds. And in the future, we want to apply this model to the galactic center. If there is a shed in the galactic center, and we know that there are stars, massive stars, close to Sagittarius A, to Sagittarius A, well, these shed-star interactions are possible in the galactic center. And also, we would like to check what happens if this G2 cloud interact with the shed